Our next example deals with the exponential distribution. This is frequently used for modeling of random waiting times. This is a very common distribution in physics. For instance, if you observe a radioactive source and you measure the times between decays, you will observe a random waiting time which is exponentially distributed. It's also a special case of the gamma distribution. So let's have a quick look in Wikipedia for the exponential distribution. So here we are. You see that the PDF is just a decaying exponential function. It has the form you see in the lower right corner. The PDF is lambda times e to the minus lambda x. In Matlab, there is a different parameterization with a parameter tau, which is the mean value, which is 1 over lambda. It's not actually called tau, but it's called mu in Matlab. So let's have a look at the PDF, the CDF, and the quantile function of the exponential distribution. Let me switch back to the Matlab window. Okay. So its name is exponential. Its parameter, which is actually the mean value, is called mu. And we set now mu to 2.5. Let's have a look at the characteristic quantities. The mean is just mu, 2.5. The variance is mu squared, so it's 6.25. So the standard deviation is identical to the mean. The median is smaller than the mean because it's again an asymmetric distribution, and the interquartile range is about 2.75. I now plot the distribution from 0 up to the 99% quantile. And you see the PDF in the top panel. The mean is at 2.5. The median is smaller. It's actually 2.5 times log 2. And we have mean plus 1 and mean minus 1 standard deviation. So as the mean and the standard deviation are the same, the violet line is exactly at 0. And mean, the green line, mean plus 1 standard deviation, is at exactly 5, because the mean and the standard deviation are both 2.5. In the bottom panels, you see again the CDF, the integral of the PDF, and the inverse CDF, the quantile function, from which you can gather the quantiles. By the way, the quantiles for levels 0.25, 0.5, and 0.75, they are called the quartiles. And the first quartile is at 0.25, the second is a median, and the third one is at 0.75. So the interquartile range contains exactly 50% of the mass of this distribution. Now I show you how to truncate such a distribution. This is frequently necessary. For instance, in my field of research, particle physics, we frequently have to truncate the exponential distribution if we measure waiting times, because for instrumental reasons we cannot measure very short, and also we cannot measure very long waiting times. So let me show you how to truncate a distribution. The method is the same for all these distributions which are predefined in the statistical toolbox. We have to define the truncation limits. And I want to truncate this exponential distribution at 0.5 at the lower end and at 8 at the upper end. In order to generate the truncated distribution, I call it distrunc, we invoke the method truncate from the object distra, which keeps the information about this exponential distribution. And this method has two arguments, the lower and the upper value of the truncation interval. This distribution has, of course, now different mean and different variance and different median than the untruncated distribution, but it is automatically renormalized to have a mass of 1. So let's now display the characteristic numbers. You see that the mean value has increased, the variance and the standard deviation have decreased. And if we compare the median, you see that the median has increased. What does this distribution look like? Well, let's try to generate a random sample from the truncated exponential distribution with the method random. If we look at this object, this trunc, we see that it is now truncated to the interval from 0.5 to 8. So this information is, of course, stored inside the object. Now let's fit an exponential distribution to this truncated data, and we'll see this is not a very good fit. So in the top end we see the histogram from the random sample from the truncated distribution. We see the true PDF of the truncated distribution in red and the fitted exponential PDF, the yellow line. And of course we see the fit is not very good, especially at the lower end of the distribution. Now we want to fit a truncated exponential distribution to the data. This is slightly more complicated because now we have to define a function handle which represents an truncated exponential distribution. And to this end, we have to renormalize the exponential PDF and then make sure that this distribution is non-zero only in the interval from 0.5 to 8. So how do we find this function handle? Well, the basis is the exponential PDF with parameter mu, and this is the function exp PDF in the statistics toolbox. Then we have to renormalize by dividing by the integral between the lower end and the upper end. This is done by invoking the function exp CDF, the cumulative distribution function. So we divide by the difference of CDF at the upper end minus the CDF at the lower end. And then we multiply by two logical vectors. So in the end, this PDF is not equal to 0 only if x exceeds the lower end and does not exceed the upper end. So this function handle represents the PDF of a truncated exponential with parameter mu. Now let me show how we do the fit in this case. This is done now in a different way as before. So we have to step into the function fit underscore dist. Now fit type is no longer a name in the list of predefined distribution. It's now a function handle. So we have to deal in a different way with this fit type. So we get the name, it's exponential. Now, this is a truncated exponential, so this field, distre point truncation, this field is non-empty, so we now know that we have to deal with a truncated exponential distribution. So we now histogram the data again. Please note the normalization of the histogram. It's normalized in such a way that it looks like a PDF, which means that its integral is 1. Now we plot the PDF of the truncated exponential distribution. This is the one from which the data were generated. And now we check whether the fit type is a function handle. Yes, it is. It's a function handle. So now we have to do the fit with this function handle, with a function defined by this handle. And this fit is now done by invoking the toolbox function MLE, which stands for maximum likelihood estimation. So the first argument is the vector of random numbers. Then we say we have a PDF in the fit type. So fit type, the function handle, represents a PDF, and we have to define a starting value for the fit. And here we can simply take the mean value of our observations. So we invoke now this maximum likelihood estimator, and we get the estimated value of the parameter, and we get a confidence interval for this parameter. And now we can plot the fitted truncated exponential PDF. And we see it's a very close fit to the true one. And we can produce a legend and then return to the main script. So we have the histogram, the true exponential truncated exponential, and the fitted truncated exponential. Okay, so this is a way to deal with truncated distributions. My final example in this script is the Poisson distribution. Now, the Poisson distribution is a counting distribution, so it takes only integer values. non-negative integer values, and it's very frequently used for the modeling of random counts. I told you before about the radioactive source. If you measure the waiting times between two decays, you will see an exponential distribution. If you count the number of decays per a predefined time unit, for instance per second, you will see that the counts are Poisson distributed. So here's the link to the web page. So the Poisson distribution is a discrete distribution. It takes only non-negative integer values. For large values of the parameter lambda, which is the mean value, the distribution can be approximated very well by a normal distribution. It has a very important property. The mean value and the variance are identical. Let me switch back to the Matlab window. So let's generate a Poisson object. Its parameter is called lambda, so the Greek letter for L. And we can set the parameter lambda, which is both mean value and variance, to a positive value. So lambda has to be positive. And we see now that mean and variance are both 3.5. The standard deviation is the square root of 3.5, and the median is at 3, and the interquartile range is also 3. So let's have a look at a graphical representation. So this is the probability function or probability density function of the distribution. You see that the distribution starts at 0. So 0 is the smallest integer with a positive probability. The maximum probability is at 3. This is also called the mode of the distribution. The mean value is 3.5, and the variance is also 3.5. I do not show the CDF and the quantile function. They are not that interesting for discrete or counting distributions. Let me now show you how to fit a Poisson distribution to a Poisson random sample. So this is a histogram of the random sample. Of course, the values are concentrated at the integers. So I will now extract the counts from the histogram. This is very important. You can extract the counts from an histogram object by the method values. Let's have a look at the methods of this histogram class. Sorry, this was not correct. This is a field of the object, not a method. Sorry. So one of the fields is called values, and this is just a vector of the group counts. So let's have a look at the counts in this histogram. and the counts are just a vector of integers corresponding to each of the groups or bins in the histogram. We can now make a graphical representation of the counts by using the function bar, which makes a bar plot. So the blue bars are the counted frequencies in the random sample. The pentagrams or stars are the values of the PDF, which you see in the upper panel. So these are just the same values as in the upper panel. And now we can fit a Poisson distribution to this data, and we can plot the fitted PDF, which is again represented by the yellow stars or pentagram. Again, we see a rather good fit. The red and the yellow values are nearly identical. So experimental frequencies, the true PDF and the fitted PDF in the lower panel. And there is a close relation between the exponential and the Poisson distribution, and this will be the subject of assignment 12.